I gave this talk on evaluating Fedora at Fedora Camp a couple of months ago, and I'm just essentially going to be talking about the same thing today, just to reach a wider audience in case it interests you. So we did this work for the Bodleian Libraries at the University of Oxford. It was Tom Roble and his team who wanted us to evaluate Fedora 6 to see if we can use it, if Oxford could use it as their digital preservation platform. And so before they committed fully to it, they wanted to make sure that it meets their needs. And so we just did the work for them. Okay, so the evaluation of Fedora 6 was broken down into two crucial parts. The first one was going to be just spend a very short amount of time just to make sure does Fedora 6 meet the requirements of a basic OCFL data store. How good is the API? Are we able to use the API as is? And does it achieve what does it achieve the throughput that we want? Does it achieve the needs that they wanted as a digital preservation platform? That was going to be the first test because if it didn't pass muster there, then we had to look elsewhere. So that was going to be the first short test we did. And in the hope that Fedora 6 met that, we were then going to go on to say we spent a few months doing performance tests on Fedora to make sure that it can be used for everyday use as a digital preservation platform. And also, it's going to be constantly used because they're going to be objects written in read from. So it's not just going to be a store that's lying, but it's also going to be heavily used. So this thinking about what are the kind of objects that are represented in our OCFL store, again, comes from Oxford. Looking at their use case, they had metadata only objects with very small files, very small binary file objects, reasonably large binary file objects, and very few of the very large binary objects and complex binary objects. But most of the system tended to have just metadata and binary files at the smaller end of the scale. And the requirements that BDLSS wanted was the most important thing is the structure of the data object should be retained within OCFL. The file should be stored in the original name. We don't want a new version for every API call, but we would like versions to be representations in time. And would we be able to achieve that with the OCFL? So this was their basic requirement. So then we ran tests multiple times in different scenarios. We had 5 different system settings that we could tweak. We could tweak settings in Java, settings with PostgreSQL, and also the number of jobs we could run in parallel. And like I said, we started off very small. The aim was to just create 500 objects and 3,000 objects and see how Fedora holds up, because here the test was to see the authenticity of the OCFL store and the ease of using the API. So the different tuning options that we chose were, the default is of course UTF-8. And then we were going to set the min and max Java heap memory to something very reasonable, like 2 GB to 4 GB, and then run tests. And then say, okay, along with setting the Java heap memory, which is like this basic, we'll also let Java know how many active processors it could use to see if that makes a difference. And then we also went with let's give Java a lot of memory and how does that affect performance. And with that, we also combined some PostgreSQL tuning with experience that Oxford had with using Fedora 3 and Fedora 4, and where they needed to do this tuning for Fedora to work well. So they wanted to know if Fedora 6 also needs this tuning and if that makes a difference. And then the last one is just a combination of the same thing. You had a lot of memory, have multiple processor counts running in parallel. What's the output? And this was going to be the distribution of the objects. Like I said, mainly small objects. Almost out of the 500, almost all 500 are tiny objects. It's just 2 KB files, or a very 2 MB, 3 MB binary object with the metadata file. And a few of the larger ones. For the 500 object, there was 5 large binary files. So these are what 500 MB in size. And a complex binary is about a few GB in size. We were not going to go for any very large binary objects for this test. And so we had 875 files across these 500 objects. The total size was going to be 32 GB. This was going to be our test. And then scaling this up to 3,000 objects. Again, a large distribution of the smaller files, but we have a few more of the bigger files now. And out of the 3,000 objects, we will be transferring 5,000 odd files, and now it's 500 GB in size. So we just did this with all the different tuning options that I talked about in the earlier slide, and ran tests for over a month just to see, does tuning make a difference? How is the API? Like we had a problem with transactions and keeping transactions alive with the large files and coming up with a way, workaround around that, all of those things. And the summary of this first part of the test was we did not need to tune PostgreSQL. It made no difference whatsoever. In our case, giving too much memory to Java slowed the system. It was significantly slower. It was as much as 60% slower. And it was much better to run Java with just 2 GB or 4 GB of RAM if you had like 16 GB and 32 GB in your server, and running multiple threads. And we found that the API works the way we expect. The OCFL object store was what was intended, and this was a setting we were going to choose for doing our large scale testing, given that we were happy with the taste of the test. Something we all know about is be aware when you're running jobs in parallel. We found that if you're running jobs when we ran 5 jobs in parallel, we got a 35% reduction in time. But when we ran 10 jobs in parallel, it took more time than running one job serially. So that just goes to show there was so much IO contention that it was just fighting all the time. So you got to be sensible about how you choose how many threads you're going to run in parallel. It all depends on what your system is, how many cores you have, what the disk IO is. And more than CPU, because this is a lot of reading to disk and writing to disk, it's the performance of your storage system matters. The more performance storage systems certainly did much better. And this was a typical graph that we came up with from many of our tests. When we ran just 500 objects with very few of the large files, most of the metadata and binary files took less than a second. And then you can see that when a large file goes, it gets clustered. But the same thing over 3,000 objects, and you have a few more of the large files. We didn't have that many, right? Just 15, that 3,000 of the larger files. And you can start seeing that even the smaller files, not all of them finish in a second now. Some of them take as much as 10 seconds to 12 seconds because of the IO contention over here. And they almost seem to go in line with the green and the pink dots where the larger files started. So that's something to be aware of. It's not necessarily, it is IO bound, and you've got to be aware of that you are using, of what IO you're using. And so then, having done this, we were going to do our testing at scale from all of the tests we did in the previous round. So in the previous round, they had given us a 1 petabyte drive. This was a scale-in drive, and that's where we did our previous round of tests. But then we found that we had a lot of issues with the 1 petabyte drive. It would crash. It would suddenly, when I queried the disk, it would say, "Oh, I've used up only 20% of the storage," because 1 petabyte is huge. But then I used to start having IO issues and saying that the disk is full and jobs failing left, right, and center. And we found that Scale-in wasn't always giving us the right number when we were querying it as to how full it was. So we had a few issues like that. So then we decided that we are going to split our test. We are going to use the old drive, which is not very performant and has issues, for creating the files that I'm going to use for these performance tests and for downloading and saving them there. But the OCFL object store itself was going to be moved onto their new storage hardware. And this was a 6 terabyte drive. And it was an NFS drive, and it had 2 processors with 4 GB of RAM. And this is how we were going to do our test. So we had 2 drives, both mounted onto the same server. And this is when we were going to start testing at performance. To start with, we were going to create 30,000 objects. By reference means I tell Fedora that this is where in file you can find the object. Please, please put this in the OCFL store. So I wasn't sending it over the network. And then we did with 400,000 objects. As you can see, the size, the total file size is the same, almost the same, 4.9 terabytes and 5 terabytes. But the number of objects, significantly different. Here there's only 30,000 objects, 60,000 files. Here it's a factor of 10 more. You have 600,000 files. Because over here, we increase the number of smaller files, just to see how does the system behave. When we have lots of small files or when you have large files, what's happening? And the same amount of data to be transferred, 5 terabytes to be written into the OCFL drive, but suddenly it's taken a good 10 hours longer, took 1.5 amounts the time. But that's not surprising because we have 10 times the number of objects. So you're having to create that many OCFL objects in disk. And then once we finished that, we finished our test when we were happy with this, we moved on to the next one, which was, again, do the 400,000 objects. And this time with a few more of very large files. And it came up to same 5 terabytes just to see how long it takes. And the significant difference over here was the system administrators with us working in Oxford noticed that, if I give you a bit more RAM and I increase the amount of CPU cores in the NFS server, not the server we were running our tests on, in the storage server, they said that's going to significantly help. Let's see if that reduces your time. So the same 400,000 objects, 600,000 files, 5 terabyte, we are back to 16 hours, which was about the same time it took for, 40,000 objects. And we did the same test again, but with a larger number of bigger files to see how much more time it takes. So we were able to write 8.7 terabytes of data in 23 hours with this NFS drive. Now that we had done the creating of objects, we were happy. This was about what the level that Oxford said this will be the maximum that we foresee in the near future. And we're happy with this amount. If you're able to transfer about 9 terabytes or 10 terabytes of data overnight, we're happy with that. And then, so now that so far we've only done creating objects. So then we did, let's start downloading objects. Let's see how does it perform. Start off small, 500 objects, just 2.5 GB. Takes less than a minute. 30,000 objects with about less than 50,000 files, 645 GB, took 2.5 hours. So now that we did this downloading objects test and we were happy with that, we were going to go on to what a typical day in Oxford looks like, which is what they call the business as usual test, which is a lot of downloads, creates and updates happen. They're distributed across, but a lot of the time we are going to be downloading files from Fedora, from the OCFL store. And how does that perform? So we had 100,000 small objects. It was 500 GB in size, the total transfer size, of which 372 we downloaded, and the remaining 130 was uploaded for either a create or a update. And this took 5.5 hours. So this time we ran 10 parallel jobs. With 10 parallel jobs, it took 3.5 hours. So significantly lower than the 5 parallel jobs. But again, just be aware that the server you run these tasks on should have enough CPU cores and should be capable of for you to be able to run jobs in parallel. Then after having done that, what we did was create, read, and update of 40,000 objects. This time we're transferring 500 GB of data, and that again took just over 2 to 3 hours for that amount of data. We went on to say, okay, 200,000 objects, but rather than 500 GB, increase it by 4 times, make it 4 TB. How long does that take? That took 14 hours to transfer 2 TB in terms of, downloading and updating and creating. And this is what a typical graph looks like when you're doing a business as usual test. And this is upload times. And you can see there's a large variation in the small files. It takes anywhere from a fraction of a second to as much as 30, 40 seconds, depending on what else is happening in the system. What other big files are being written or downloaded. Yeah, and this is our experience with Fedora, and I should say Oxford were very happy, and it meets it more than meets their needs for now and for the near future. I'll stop sharing and take questions.
Awesome, thank you so much. Yeah, we have some time for questions if people have.
Hi. Thanks, Anusha. That's very useful. I was just going to ask about OCFL indexing time. So the time it takes Fedora 6 to index.
It wasn't significant.
Yeah.
So as you could see, we could once we created the objects, we were able to download them pretty fast. Significant, just 2 hours, and you could download a significant amount of data. So the indexing time wasn't significant at all.
Okay. And do you triple store index these as well?
No.
Or Solar? No.
No, we didn't triple store index these. We didn't put these to Solar because this was just going to be their preservation backend because they were going to use their repository Aura, which was going to do the indexing in the everyday business.
Understood. Great. Thank you very much.
Welcome.
Doran, question?
Yeah, hi. Thank you for the presentation. I was curious about the part on where extra memory resulted in worse performance. And so I'm wondering how much physical and virtual memory were on the system, and if maybe you had thoughts on the reasons for the worse performance with more memory. Thank you.
So what we observed was it depends on the balance of files you have. If you're going to be working with large files, having a lot of RAM actually helped. But in our case, it wasn't large files. It was predominantly 2 KB metadata files and a few MB binary files. So over here, what was happening is the sheer number of times we were having to read and write rather than just keep sending in chunks of large files. So it all depends on what your distribution is. I would say if your distribution is going to be many large files written, certainly higher memory helped. But if you're going to be writing many small files, it didn't. It was counterproductive. And it wasn't virtual memory, it was actually physical RAM that they had.
Thank you.
Any other questions? Yeah, Jaime. Oh, we don't have audio, sorry.
Oh, sorry.
There we go. Mhm.
I'm not sure if I saw that on the presentation, but I would like to ask you about transactions. Do you have any experience with the transactions and the results of them?
Yeah. So we struggled to keep transactions alive when the files were even 500 MB in size. And for the ones that were multiple terabytes in size, it was challenging. So we came up with the we came up with a workaround where we had a separate shell script, and all it was doing is pinging Fedora and saying, "Hey, this is a transaction ID, keep it alive. This is a transaction ID, keep it alive." And once we were confident that the file's finished uploading, then we used to stop that. So we had to come around with our hack around to actually make the transactions stay along. But otherwise, yeah, they kept failing left, right, and center.
Thanks.
Other questions? Okay, so with that, thank you, Anusha, for that awesome presentation.